Now, children, for today, I am going to discuss with you Lenz's law. What is this Lenz's law, children? Look at this heading, Lenz's law. And to start this topic, Lenz's law, I want to take help of this diagram, induced EMF and current in a coil. Now, from the previous lesson, it is understood that, children, the EMI phenomena, electromagnetic induction. Here in this diagram, children, on the screen, you can see a coil is there. Many turns are there, okay? And the magnet is there. Look at the sign of arrow of this magnet, children. This sign, it indicates that this magnet is not stationary. It is moving, it is approaching and or trying to insert in the coil. Magnet is in motion. Magnetic flux lines are keep changing and changing. They are cutting in the coil. They are passing through the coil. And current is there. Current is there in the coil. You can see that the current is there in a coil. Now, children, what is this Lenz's law actually? Lenz's law helps us to find out the direction of current induced in this electromagnetic induction phenomena. To find out the direction of current, as again, children, we are talking about a coil, current in a coil. So then the current either will be a clockwise or in anti-clockwise direction. So Lenz's law helps us to predict the direction of current induced in a coil when a magnet is moved towards the coil or away from the coil. Now, one more point about the Lenz's law is that, children, we know from the discussion of electromagnetic induction phenomena, current induced in a coil. EMF is there, a voltage is there. If voltage is there, current will be there. And Lenz, this scientist, this is the name of scientist, okay? Lenz's law. He explained that the current will induced in a coil in such a way. Let me repeat my word, children. Current induced in a coil in such a way that it can oppose the factor which is responsible for the current to induced in a coil. One more time, children. Listen carefully. It will take some time, but then you will understand it. Have patience. Let me repeat. Lenz states that current induced in a coil in such a way, children. It's not always a clockwise, it's not always an anti-clockwise. In such a way that it can oppose. What oppose? It can oppose the factors responsible for to induce current in a coil. Now, what is the factor? Or what factor is responsible to induce a current in a coil, children? Ethan, what factor is responsible for that current is induced in this coil? Who is responsible? And class students, anyone? If someone asks you that if this question comes in exam, in a coil, when you're moving a magnet, current is inducing. So what factor? The answer is, children, the simple answer is the changing magnetic field lines. The magnetic flux which are, as the magnet is approaching towards the coil, this change in magnetic field lines when magnet is moving towards the coil. So Lenz states that the current will induce in such a way that it can oppose over that the magnet don't come near to me. Don't come near to me. And this is a very famous idiom, actually. It's not a proverb, it's idiom. Biting the hands that feeds you. Biting the hands that feeds you, children. This idiom is working here. In Hindi, children, that the Indian student that they can understand. In Hindi, that this idiom is like, jis thali mein khana, us thali mein ched karna. Biting the hands that feeding you. Now, current induced in a coil by the movement of the magnet towards the coil. But this Lenz's law, he states that the current adjusts in such a way that it can oppose the creator of the current in this case. How? Let me explain now, children. So now, children, here in exams, that this is the solved question that already they have mentioned the direction of current in the coil. This you can see they mark the current here, but forget for a moment that there is no direction of current. In exams, you will find that this part is given, magnet is there, coil is there, and then you have to predict these signs of arrow will be upward, downward, means upward, downward means in the coil, it will be clockwise or anti-clockwise direction. Now, let me help you. How would you find out that this current will be clockwise or anti-clockwise? Remember that what law is helping you? Lenz's law will help you to find out the direction of this current. And how? Let me explain. The meaning is simple, that it will oppose. Magnet is moving towards the coil. Magnetic field lines, more and more magnetic field lines are crossing this coil. Now, Lenz states that it will automatically create a current in such a way that it can oppose. So, let me use the red pencil. It will create a north pole here. Automatically, a north pole will be there, as per the Lenz's law. Now, why do here we have a north pole, children? So that it can oppose the motion. North and north will repel. This magnet is coming towards the coil. The magnet is coming towards the coil, and on the coil, you will find that the north pole is there. So north and north will repel. So if repulsion is there, then what will happen? Then the magnet will try to go away. That it will go away. So if north pole arises, then the simplest rule that we already discussed in previous lesson, children, if it is a north pole, then the person at the observer, means the observer towards the magnet side, will find the current in the coil is anti-clockwise direction. That's why this sign here. This is the anti-clockwise, children. This is the anti-clockwise direction from the observer looking from the magnet side. Now, suppose if you are saying that, okay, sir, that this part is okay, but what happens if this magnet is moved away? That the second diagram here, children. If the magnet move away, what happens? How the Lenz's law will give you the direction of current. Again, remember the statement of the Lenz's law. It always opposes. Now the magnet is going away. Magnet is going away. Now magnetic field lines, again, they start crossing the lines or the coils. The magnetic field lines, they are now varying in the term that it is now decreasing as the magnet is going away from the coil. Again, the current is induced in the coil. In both the factors, whether the magnet move towards the coil or away from the coil, current will generate. Current is generated. But what direction? You have to predict. You have to take the help of the Lenz's law. If the magnet is moving away from the coil, now it will create a south pole there. Why it will create a south pole? Because it cannot oppose the motion. Because now the magnet is moving away, it will have to create a south pole so that it can attract the magnet, so that it won't move away. It will attract it. It will attract it. Now, initially, what happens, children? Here it is repelling. It's a rebellion. It's repelling here. Don't come closer to me. In the second case, where it is going away, Lenz said that now the coil will create a pole in such a way that it will try to attack. Then it will say, don't go away from me. Don't go away from me. Come closer to me. Be here. Don't come very, very closer to me. Don't go away from me, but be here. Okay. So if south pole is there, children, what happens? South pole means that the direction of current in the coil will be in the clockwise direction. So you need to draw the clockwise direction in the coil, and this is the clockwise direction from the observer at the magnet side. That's the Lenz's law. Any other case I can take now? Let me go to the whiteboard. Remember this. I will take some other case. Another case that if the south pole is moving towards the coil. Okay. So south pole example is not in the book, so I need to draw. Let me take. This is my coil. Galvanometer is attached, sensitive device, galvanometer, and magnet is again. And so this time I'm taking south pole, or the magnet is near to the coil, and magnet is in motion with velocity v. And the magnetic field lines, children, again. Remember, this is the south pole, and the sign of arrow these magnetic field lines are coming from the north pole actually, that I'm not required to show that lines here. Magnet is moving towards the coil. I know that the current will be there in the circuit. EMI phenomena that I already explained by the Faraday. Current is there, but direction, you need to find out the direction. Current, hi children. Sometimes in the exam that the question will be find the current direction, and sometimes they will ask you whether what type of pole will be there, north pole or south pole will be there, to the left side or to the right side of the coil. If I get any one answer, then I will get the other one also. So south pole is moving. Lenz's law said it need to oppose. Current will be in this coil in such a way that it can oppose the motion of the magnet towards the coil. So to oppose the motion, I need to, means this south pole automatically great here. I'm writing this south here, but it automatically will be there. South pole will be there. Basically, south pole means nothing, but it is the current which is there. Current, what current? Clockwise direction of current is there. So clockwise direction, let me write like this, children. Don't forget, don't get confused, children. It's a clockwise direction. Okay. So clockwise, south pole is there. In the another diagram, again the same question, but again north south coil, same coil, kilometer, and but now the magnet is going away. Remember, don't forget to draw the magnetic field lines. Magnet is going away. So now children, may I know the answer? Current in the coil will be clockwise or anti-clockwise. What pole will be here? North or south pole, children? Anyone from 10th class, please. I want to hear from you, children.
North.
Yash, Yajesh, Hibanshi, all of you, please try, children. If you have doubt, children, then say, sir, please repeat this topic. I will help you. Calista said it's a north pole. Yeah. So I got few answers. And north pole will be here. Now, why north pole is there? Someone asked you why north pole is there. Then you have to look, you have to explain to that person who is asking why north pole is there, that you should know about the Lenz's law. You know, it's a simple topic, children. If the magnet is moving away, Lenz said that it will oppose. You know, when the magnet is going away, again the current is inducing in the coil, and Lenz said that it will induce current will try to oppose the factor which is responsible for the current to induce in a circuit. And what is the factor? That factor you have to understand, children. Callister, you have to understand what factor is responsible for the current induced in this coil. And the factor is change in flux, change in magnetic field lines, or change in flux. What do you mean by flux means? Flux means, children, number of magnetic field lines. Number of magnetic field lines crossing or passing through a coil, or cutting or cut a coil. So as the magnet is going away, the magnetic field lines, they are varying, they are going, magnet is moving away from the coils, then the magnetic field lines again they start crossing the coil. During this crossing the coil, you know what happened? During the variation of the magnetic field lines, or during the variation of the flux lines, what happens? Current induced, that is the EMI. Changing magnetic flux is responsible for the current to induce. So now current is there, but now what direction of current? Clock or anti-clockwise? To find, you have to use the Lenz's law. What the Lenz's law? It always opposes the motion. Always oppose the motion means if the magnet is going away and the south pole is there, so definitely, or it is obvious that it will create a north pole here, so that the magnet won't go away. Because it is going away, it is creating the current. It is inducing a current because the flux is changing. And in this case, what happened? Again, when the magnet is moving, again there is a change in magnetic flux. Field lines are crossing the coil. Again, the current will be there. in such a way that it can oppose the motion. Oppose the motion, it need to create a south pole here, so that there will be repulsion. So that this happens, this phenomena continually repeating and repeating itself, that sometimes the current will be clockwise, sometimes this current will be anti-clockwise in direction. Okay, let's look some question. Then you will understand the meaning of this topic. Okay, let me begin from the question number 1, children. Please read it yourself and then try this question, children. Question number 1. And let me help you. You keep doing by yourself also. Wire on the right forms part of a circuit. When the wire is moved, where? Downwards. They said the wire is moving downward, that's the red sign here. A current is induced. Okay, current is there. What would be the effect of now point number A, moving the wire upwards? If you make the wire to move upwards, what happens to the, what would be the effect of the moving the wire upward through the magnetic field? If you make the wire, initially it is downward, a current is induced. What would be the effect of the moving the wire upward through the magnetic field? Basically, they are looking for what happens with the current.
The current will change.
Current will change. So change word you can use. Current get reversed. Okay, means if it is entering into the laptop screen, it will change its direction, that it will reversed and it will come out from the screen. That is the meaning of this question, children. 1A. B part. Holding the wire still in the magnetic field. Holding a wire. Holding a wire. Holding the wire. There is no motion. They are saying holding a wire. Velocity is 0. No motion in the wire. If there is no motion in the wire, yes, please. Who is saying?
No current.
No current. No current will be there, actually. No current or EMI is there only if either one of the factors should be in motion, either the coil or the wire or the loop or the magnet move. C part. Moving the wire parallel to the magnetic field. Means wire is going in this way, in the direction of magnetic field. So if the wire move parallel to the magnetic field, in that case, theta we consider either theta is 0 degree, or if it is anti-parallel, then theta is 180 degree, and sin theta, sin theta, actually sin 0, 0, sin 180 is also 0. And in that case, what happens? Moving the wire parallel to the magnetic field lines, no current will be there. So this is question number 1, children. Now move to the second. Second question is, in the experiment at the top of the page, what would be the effect of moving the magnet faster? Top of the page. What diagram is there at the top of the page? I think this one diagram. So if they're saying if you move the speed or velocity of the magnet, what changes it will make in the coil, in the current?
Current will increase.
Greater, more electromagnet.
Yeah, more electromagnetic induction means that you can say that the more current will be there, or strength of the current will increase, moving the magnet faster. Second point, turning the magnet round so that the S pole is pushed into the coil.
So what does turning the magnet round mean? Like
Turning the magnet, that they change the pole, so now the south pole is pushed into the coil. Instead of north, now they're saying turn around means, they're talking about turn around, that now south is here, north is there. Then what will happen in the current? And yeah, then again the south pole will be there, repulsion will be there, Lenz's law will be there, and if the Lenz's law is there, south pole there, then the direction of the current will be in the clockwise direction. Clockwise direction. So that is answer for that question. Having more turns in the same diagram, increase the number of turns. Number of turns will make, it will help here. It will help to, still current is there in the same direction, whatever the current is going, but it will make now higher current will be there if you increase the number of turns. Again, the concept is simple. Increase in number of turns means will make that more and more negative field lines then can pass through the coil. I think that I am talking about this clockwise or anti-clockwise. Now, listen here. Suppose in this case, if I take the present case, children, north pole is moving, north pole of the magnet is moving towards the coil, then I know that the north pole will be there. Is this clear? I think north pole will be there or not? First tell me.
Yes, sir.
Yeah, north pole will be there. Okay. So north pole will give you the anti-clockwise direction. That is the shortcut that you can remember, memorize. If north pole is there, then the direction of current will be anti-clockwise. Otherwise, you can remember, recall that the right-hand grip rule we discussed in the beginning of the chapter. And right-hand grip rule, I told you, thumb in the direction of north pole, then the fingers, curling of the fingers, that will give you the direction of the current in the loop. So my tip that is going upward, so that's why the sign of arrows in this loop is in the upward direction here. I hope this part is clear until now. And suppose if this magnet is going up, take this case again, north pole is moving away, south pole will be there, south pole is there. Then what will be the direction of the current? South pole will give you clockwise direction. You have to draw the current clockwise. And again, you can apply what rule? North pole. If south is there, definitely the other side, the north pole will be here. North pole. If north pole is there, again, the right hand grip rule, you have to point the thumb in the direction of the north and the curl of the finger. Now the finger, they are, the tip are downward. So that's why these sign of arrow. It's actually not downward, upward. Actually, this is the clockwise direction. Clockwise direction for what? For the observer here.
Yeah, got it, sir.
Okay, thank you. Good. So this part is done. This one. More about induced current. This is the same children that we already discussed. 9.08 is the same topic that we already discussed. Yeah, that even you can read this line here about the Lenz's law. This one, children. An induced current is always flow in such that it opposes the change which produced it. Again, you can see that this is also the same right-hand grip rule to find the direction of current in a loop. But before that, you should identify in what direction the north pole will come, where south pole will come. This topic we already discussed in the last lesson, children, Fleming's right-hand rule. And okay, now look at this exercise, question number 1. Look at the diagram on the opposite page, illustrating Fleming's right-hand rule. If the direction of the magnetic field and the motion were both reversed, how would this affect the direction of the induced current? This kind of question are also very important, especially for the MCQ. Look at the diagram on the opposite page. I will go to the opposite page, but before that, Fleming's right-hand rule. If the direction of magnetic field and the motion, they have changed the two factors. Magnetic field is changed, motion of the wire changed. What would be the change in the direction of current? On the opposite page, they are talking about this diagram. In this case, children, what are they saying? Motion has been changed. Instead of moving up, it is downward. And the magnetic field is changed. Magnetic field change means now they have interchanged the pole. Now north pole is there, south pole is there. The direction of magnetic field is like this. What happens to the current? The current in the coil, you can see here. That I can see this is something around anticlockwise. If I change both the factors, what happens? You apply the Fleming's right hand rule. Motion is downward. Look at this. Okay, let me use the blue ink. Conductor motion is downward, and magnetic field is north to south. Apply Fleming's right hand rule. Motion is downward, so thumb should be downward. Thumb should be downward, children. Okay, and the first finger, that for the magnetic field. Magnetic field is in where? Inward direction, north and south. So magnetic field is from left to right. I need to change my position. So thumb is still the motion of the conductor downward. The magnetic field is now north to south. My finger, that the middle finger, I can see it is pointing towards me. It is pointing towards me. If it is pointing towards me, then what happens? Still the same. It is pointing. The current in the coil here. This is again. It is pointing towards me. So last time I think I have explained. If you change both the factors, then there will not be any change in the direction of current. But if you change any one factor, if one factor is changed, either direction of magnetic field or motion, if one factor is changed, children, then current get reversed. Direction of current will get reversed. So here, if I say only one factor is changed, then this conductor current, this, look at this sign of arrow, children, here, this will reverse. So instead of down, it will be like this. So this kind of will be a clockwise current. Remember, children, I hope that you are getting my point, what I'm saying here. If magnetic field B and another factor motion, both are changed, both are changed, then there will be no, the result of it is no change. There will be no change in direction of current. However, if one factor changed, only one factor, only one factor, only one factor changed, then I get reversed. Means whatever the direction of current is given, so in that case, I get reversed. The information which I have written here, children, you can check it by using the Fleming right hand rule. Both factors change, no change in the direction of current, whatever the direction of current is suggested in the question. If one factor change, then direction of current will get reversed. Okay, that's the topic, children, that I want to discuss with you today. And question number 2, we can also try. On the right, a magnet is there. Current is induced in the coil. Definitely current will be there according to the Michael Faraday. EMI, electromagnetic induction, is there. What type of pole is formed at the left end of the coil? Give reason for your answer. Yeah, 10th class students. What pole? North or south? Apply Lenz's law. Opposition should be there. May I get your answer in chat box, children, please? Send your answers. North or south? And explanation.
Sir, question 2.
Yes, question 2A part. I received answer from Yash. He said south pole will be there. Definitely it is the south pole will be there. Opposition in the current will be in such a way, yes, Abhishek, good, that it can oppose the motion of the magnet. Oppose the motion of the magnet, definitely south pole should be here. So that the repulsion will be there. And if the south pole is here, children, okay, one more answer I see. As it moved, as it would repel the magnet as magnet is moving towards the pole. So by inducing a south pole means the current, you have to look for the direction of current in the coil in the clockwise direction. Okay, children, clockwise direction. And if the direction of current is clockwise, so south pole will be there. On this side will be north pole. Reason, what is the reason for it? Explanation of Lenz's law you have to write. So that according to the Lenz's law, current will be in the clockwise direction so that it can oppose the factors which is responsible to induce a current in the coil. Similarly, you can also find the direction of current, B part. What will be the direction of the current? That already discussed, it is a clockwise, whether it is A to B or B to A. Now, children, in next class, we will be going to talk about generators. Generators, okay? Generators to generate current, alternating current. So now in the next meeting, children, I'm not going to take any other topic.